Buslaev teach me mathematics, so it's a pleasure for me to give this talk on this conference dedicated to the memory of Buslaev. And I'm grateful to the organizers for the invitation. In my talk, I would like to consider the compact Riemannian manifolds, and the question is how uniformly can points be distributed on this manifold. The simplest Riemannian manifold compact is the sphere. And for sphere, this problem was solved many, many years ago by Beck, Joseph Beck. And the problem was to extend this result to arbitrary Riemannian manifolds. Unfortunately, it was not done because the problem was to investigate the balls in these spaces in details. And it was difficult because the structure of balls, if they are small, then I very simply constructed for the Riemannian manifolds. Actually, this is the definition of the Riemannian manifold as a set which constructed in locally like Euclidean space, and balls, small balls in the Riemannian manifolds are the same as balls, small balls in Euclidean space. But when the radius increases, then the structure of this ball becomes more and more difficult. And the problem was to describe this difficultness. Okay, so let's give some definitions to be concrete. So we consider metric space. So Riemannian manifold can be considered as a metric space with fixed metric theta, which is simply the Riemannian metric in this space, and measure as a Riemannian measure on it, because the Riemannian manifold contains a smooth structure and metric tensor on it, and all these things, metric and measure, can be easily defined. It's standard things. So we consider a little more general situation when M is a compact connected metric space. So we are ignoring now the smooth structure on the space. We consider balls, their definition are written here, and now we define the discrepancy of an n-point subset given in this space. So we consider the real number of points. Oh, sorry, how to switch in this? Can you explain me how to no, nobody?
Вот эти вот две.
А как, чтобы...
Попробуйте нажать, да.
И что?
И что, не получается?
Nothing.
Эти. Вот эти. Вот это и вот это. Вот это.
Чтобы указка-то была?
Чтобы указка, наверное, вот это.
Вот эта вот кнопка между ними. Вот красненькая.
Кнопки красные между ними.
So we calculate the real number of points inside the ball, and minus the expectation of this value, volume n times volume of this ball, and this is by definition this is the local discrepancy. Okay, next. Okay, sorry. Now we can. This is a function. This is a function of radius and the center of the ball. X is the center. Ball is centered at X. So, no. So this function, we can consider now several norms of these functions. For example, P norm of this function with respect to radius and with respect to the center. So the measure on the, this is the standard measure on this space given originally, and psi is some other measure, finite and normalized on the set of all radiuses. So I'm sorry. And we define the supremum norm also. I'm sorry. So we define the supremum norm also, and now the extremal LP discrepancies are defined by the following formulas. So LP, we consider the discrepancy LP for a given D sub n, and then consider the infimum of this quantity with respect to all possible distributions of n points. Okay, next. Main results. Now we specialize the metric space, this, with the following condition. So the radius, so the volume of small radiuses, radius satisfies this bound, two-side bound. And these spaces are known as L-force regular spaces. And of course, the Riemannian manifold satisfies these bounds because actually it satisfies the asymptotic behavior of this order. If the D, where D is the dimension of the manifold. Another condition is more specific. So we suppose that the volume is Lipschitz continuous. So this inequality is satisfied for is satisfied for all points and for all radii. And this constant here, the constant here is independent of y, the center of the ball. If so, I'm sorry. What is the next? And okay, let me consider. The main theorem is the following. So suppose that our metric measure space satisfies conditions A and B. Then for all n, we have the following bound for LP discrepancy for finite P. And it's important here that this dependence of this exponent is given explicitly, and the behavior, the degree of n is also given in this form. Okay, so and this bound is sharp for these exponents if measure is absolutely continuous, and the measure on the set of radii. And this is known also that this bound is best possible if n is large for special spaces like this. Sorry, for the spheres, d-dimensional spheres, Euclidean spheres, for real complex and quaternionic projective spaces.
Maxim, could you repeat what is lambda p?
This, you mean this p?
Lambda p.
Lambda p. lambda p. It's here given. Seems so. Is it okay? Lambda p. So we calculate this norm first, then we change dn, the set of n points in this space, and consider the infimum of this quantity. So this is the best possible distribution of n points with respect to the norm, with respect to the LP norm. So, okay, so this is very good bound. Actually, the best possible for many spaces, for specific spaces like this mentioned here, for spheres, for example. It's too hot. And the problem is whether the conditions A and B are satisfied for Riemannian manifolds, for all Riemannian manifolds. The first condition, as I told you, is adversely satisfied. But the question is about this condition. And fortunately, it's true. It's true. It's also true both conditions A and B are satisfied for arbitrary d-dimensional Riemannian manifold. Okay, now some comments on this theorem. So this solves the problem that I begin with. So for arbitrary Riemannian manifold, this bound is valid, and this bound is the best possible for at least for these manifolds. It's an open problem whether or not this bound is the best possible for an arbitrary Riemannian manifold. But it's known that the condition that the measure, this measure is absolutely continuous, because for singular measures and for spheres, it's known that this bound can be improved, even replaced by a constant, independent of this exponent. But it's very strange thing, and it is connected with the fact that sphere is very symmetric space. Okay, now some comments probably. How to prove this theorem? Okay, about L infinity norm. Let's say, it turns out that L infinity norm for discrepancy can be estimated from above by LP norm for arbitrary exponent with and M is an arbitrary parameter. Actually, M is an arbitrary parameter. So if we choose this value of this parameter, then we get this bound, and using the theorem that was proved. And next we choose this P as this quantity. As a result, we obtain the following result, that L infinity discrepancy, extremal discrepancy, can be estimated by the same factor times the logarithmically large factor only. So L infinity discrepancy is about the same as LP discrepancy. And for spheres, this bound was also proved by Beck in 1984. Additional remarks. These authors proved this bound, the same as was stated before, under very special condition. For Riemannian manifold M, we can define the d-dimension. We can define Rm, that is injectivity radius. That is, let me explain. If we consider balls in Riemannian manifold, then if ball is sufficiently small, then it's diffeomorphic to the standard ball in the Euclidean space. But then if radius is large, this ball becomes a very complicated so is it defined? So the Rm denotes the minimal radius such that all balls smaller radius are diffeomorphic to the Euclidean ball. So this is maximal radius where the structure of the Riemannian manifold is equivalent to the structure of Euclidean balls, Euclidean space. So they proved that LP norm is the standard bound if the measure is concentrated on subinterval, on this small interval. For p equal to infinity, one has this bound where this L infinity discrepancy is defined by formulas before, but infimum here is taken only for small r, or on small r. So smaller than the radius of injectivity. For compact manifolds, the radius of injectivity is positive. It's clear because it's positive at each point, at each ball centered at a given point. Then this ball is diffeomorphic to the Euclidean ball, because so it's positive at each point, and because the space is compact, it's positive for all the space. For some spaces, radius of injectivity can be equal to the diameter of the ball. For example, for the sphere, it's clear. It's clear because it's sphere, all right? And this is a point. And we simply take this point out, and then we can consider all this space, this sphere without this point as a disk in the d-dimensional space. So radius of injectivity is equal to the diameter, and that is why the result of Beck was proved many years ago, because analysis on the sphere, geometric analysis was more or less easy. It was clear from the picture how all things are constructed there. For other spaces, it becomes a little more difficult, but for projective spaces, it can be also given. It can be also given, as I told about. Now, and now about the proof. about the proof. The proof is based on the following partition of the space into subspaces of equal measure and small diameters, of that order. So for each n, it turns out, and it is not a trivial theorem, rather deep theorem, that each metric space, compact metric space, can be divided into disjoint. For each n, we can consider, we have a space, compact space. Then for each n, this space can be divided into disjoint union of n subspaces of equal measure, and we suppose, of course, here that the total measure of the space M is equal to 1, normalized by 1. And small diameter of this order, they are the union, disjoint union, and diameters of these subsets is of this order. Okay, this is a very interesting result, and the proof is very non-trivial. Not difficult, but non-trivial. Okay, then we simply construct the following distribution. We consider points precisely in these parts of the partition, and then we let them to be uniformly distributed in these sets of partitions, and consider the discrepancy of such point sets, and it's a random variable that can be written in this form, and where these quantities are random variables which are independent. If points are randomly distributed in these sets independently. As a result, discrepancy, the local discrepancy is the sum of independent variables, and we can apply Marcinkiewicz-Zygmunt inequality. Oh, I'm sorry, Zygmunt should be written with y instead of I. Okay, so this is Marcinkiewicz-Zygmunt inequality. If we have a sum of random variables, independent random variables, then expectation of this quantity of this sum can be estimated like this, with precisely given constant. If we apply this inequality, we obtain that expectation of discrepancy as a random variable can be estimated by this thing. And if expectation is such, then there is a random subset, a random distribution, which satisfies the bound that was stated here before, So there is a distribution which satisfies this random distribution that satisfies this bound, and it proves this bound. It's typical trick when random variables are used to prove some, some combinatorial object. We consider a family of such objects. In our case, they are distributions, and they are random, and if expectation is estimated somehow from above, then it means that there are distributions satisfying the bound like this. Typical trick in combinatorics. Okay, so it reminds to prove what? That Riemannian manifolds satisfy the conditions A and B, especially the condition B should be checked. Actually, the message of this consideration is the following: that just a moment. So let's return to analysis of these sources. They reduced the bound. Why they were restricted by small balls only? Because they investigated the discrepancy and reduce the proof of this bound to analysis of the surface of the sphere in a given Riemannian manifold. The structure of this surface is very difficult if radius is large. If it's small, it's simple. It's like a sphere in the Euclidean space, and all things can be calculated. But if radius increases, then the structure becomes very difficult, and it's difficult to analyze all these things. But in the approach I describe, we reduce the analysis of discrepancy to the volume, because the singularities on the surface and on a sphere have measure 0 and can be eliminated more or less easily. So the message of this consideration is that if we consider this problem, if we consider, of course, this problem from a distance, from a large distance, you see nothing. But also, if we begin to consider this problem very close to it, we meet a lot of details, and it's difficult to analyze all these details. So the appropriate distance should be chosen to analyze this problem, and the main result here is that conditions A and B guarantee that this bound holds. So actually in this theorem, we reduce the analysis of discrepancies to analysis of the volume. So only volume controls the magnitude of the discrepancy. No analysis, no geometric analysis in the neighborhood of the surface of the sphere, but only the volume. But volume is more or less regular thing, even for arbitrary Riemannian manifolds. It is, and we need. Okay. Unfortunately, at this point, my computer stopped and refused to product these transparencies. And so I have to write few formulas here on the blackboard. Okay. So how to prove that the volume on the Riemannian of the ball on the Riemannian manifold is a Lipschitz continuous function of radius. Let's consider specific non-compact manifold like hyperboloid. Something like this. it's a space of constant curvature, of constant negative curvature minus k. And the volume of ball of this in this space can be given by the following explicit formula. It's sigma d integral r is sinus d minus 1 do. Okay, this is the ball. This is the ball, for example, of hyperbolic radius r, and this is hyperbolic sign, and this integral, and sigma is the volume of the unit ball in the d-dimensional Euclidean space. It's explicit formula, it's known, yeah. Now, we need the following remarkable result, lemma. It's a special case of the Bishop-Gromov theorem. It says that for each compact Riemannian manifold, there exists a constant depending non-negative constant depending only the manifold, such that the for all such that for all k the following thing, we are y divided by vk r. This volume, by the way, this volume doesn't depend on the position of the center of the ball, because this is a very homogeneous space here. The translation, it is a group of translations, and this is invariant, yeah, of translations. So we consider this such that for all k sufficiently large, this ratio is monotonic, non-increasing function of non-increasing function of r, which tends to 1 as radius tends to 0. So this is a monotonic. So we compare the volume in our Riemannian manifold with the volume in this specific hyperbolic space, and it turns out this volume for arbitrary manifold, Riemannian manifold, can be controlled by this thing. So if we consider R1 positive, R2, and smaller diameter, then from this lemma we obtain R 1 R 1 okay R 2 R2 smaller than 1. So for arbitrary R1 and R2 we have these inequalities. Actually Bishop proved this inequality. So this volume is always smaller than this one. And Gromov improved this result, proving that we have additionally this inequality, monotonity. From here, we obtain the following inequality. We are to 1 is it? I'm sorry. It should be 2 here because this is non-increasing function. Non-increasing. So if R is bigger, it should be smaller, yeah. It should be smaller. All right. So we get the following. It's V1 V K R1 V K R2. So so it's okay. R1 and it's smaller, and then R1. So these inequalities imply these ones. Is it clear? I hope. If so, the result we need follows, because this function is monotonic and smooth, is given by this formula. Of course, it's Lipschitz continuous. Therefore, that one, that difference is also Lipschitz continuous. This proves this result. So I can repeat again that this problem has to be studied not in much details to be solved. So we have a ball BRY of radius R centered at Y in our space M. And we also have n-point subset.
In the ball,
No, in M.
just on M.
In M. It doesn't depend on balls, on any things.
Some point subset.
Yeah, and any point subset of n points. Now we consider the number of these points in the ball. All right? And if they are more or less uniformly distributed, this quantity should be proportional to the volume. The more volume of the ball, the more points fall inside.
Of D.
Sorry?
To the volume of what? Of D.
Of intersection.
It's an intersection. Intersection. Oh, so there is our M, then point. Now we consider the ball. This is B. And we calculate the number of points that are inside. Okay? Now this is the quantity. This is the quantity. Now we consider minus and volume B Y. And compare this one and this one. And point set, by definition, is uniformly distributed if this quantity is small with respect to n. We can consider, okay, n minus 1. If they are distributed uniformly, that is proportional to the volume, and this is, it tends to 0. If it tends to 0, the point sets for large n. This point sets more and more uniformly distributed. Is it clear?
Yes.
Okay.
Just one question. Why is it called discrepancy? Discrepancy between what and what? You mean the
Discrepancy between this and this, yeah.
isn't large?
Large?
Yes.
How large is it?
Is it assumed large or it can be 1? N.
N?
N может быть единицей или большое.
N tends to infinity. N tends to...
Up to you.
Okay.
Yeah, but some people study if n is equal to 1, but dimension is high. But it's pathology from my standpoint.